Hello, my name is Greg Maples. I'm a senior security architect at Gigamon, and this topic is a deep dive into TLS 1.3. For this conversation today, we're going to review the SSL TLS handshake in detail, issues that existed with TLS 1.2, the reason that, in other words, the reason that we progressed to TLS 1.3, and we're going to go into the TLS 1.3 handshake. TLS and SSL, its predecessor, exist at the transport layer. They're not a network layer, and they're not an application layer technology. They exist as an encapsulation technology between TCP and higher level protocols. The math behind encryption, SSL, TLS encryption, is asymmetric. And asymmetric encryption is several orders of magnitude much more computationally expensive than traditional symmetric cryptography. What does asymmetric encryption mean? It means that the two parties to the session have two separate keys. Each has an encrypt key and a decrypt key. The sender has an encrypt key for the receiver. The receiver has an encrypt key for the sender. And that way they are able to send and receive, but they don't both know the same information. So the question is SSL TLS asymmetric or is it symmetric? Well, first it's asymmetric during the handshake phase, and then because it's so computationally expensive, it becomes symmetric when session keys are exchanged for symmetric, much lower cost encryption. So TLS 1.2, roughly the phases for session establishment are agree on the protocol and version, agree on the algorithms, exchange and validate the certificates, use asymmetric encryption technique to generate the shared key, and then finally when the handshake is complete, you can actually begin the cryptographic exchange. So diving into TLS 1.2, the SSL handshake, the client hello. The client hello message, and for each of these slides, and these slides will be available to you, there's Wireshark examples that you can read through. I'm not going to do that in detail during this presentation, but this information is available to you and you can dig into it deeper on your own. So the client hello message contains a version. This is the TLS protocol version that the client wants to use. A client random, which is 32 byte, not 32-bit, 32 byte pseudo-random number that's used in the later calculation for what's called the master secret. The session identifier, which is a unique number from the client used to identify a session. Cipher suite, the list of cipher suites that the client knows how to use or would like to use, and then a compression method, if any, that the client would like to use. Continuing, the client hello message can optionally contain a certificate status request, which means please include a certificate status along with the certificate when you reply to me. This, why would the client do that? That allows the client to reduce the number of exchanges and load on itself to side fetch the certificate status message. So then the next piece is the server hello. The server hello comes back from the server after the client hello. The server sends multiple messages to the client. So there's a CCR, then there's the certificate status, the server key exchange, and the hello is done. So we'll go through that. So the server version, so the server hello says this is the TLS version that I can use. So yes, we can use TLS 1.2. Here is my 32-byte pseudo-random number. So now, once this is complete, both sides have a 32-byte pseudo-random number generated by the other. Using that information as well as other information, they can create a unique what's called pre-master secret, but more on that later. There's a session identifier. That's a unique number to identify the session for the connection to the client. If the session ID in the client hello message wasn't empty, the server is going to look in its session cache to see if it can find a matching session, because the client is requesting to pick up at a pre-existing session. If the client hello session identifier message was empty, then this is a new session. Then it's following, the next piece is the cipher suite. So this is the strongest cipher suite descending order from the server that the server would like to use. And then the compression method that has been agreed upon by both the server and the client. Optional components of the server hello is the client certificate request called the CCR. Is optional, sent when the server wants to authenticate the client. So in other words, if, for example, a website where server needs to confirm the client's actual identity before the client is allowed to connect. This is an optional and unusual component of the SSL handshake. The next piece of the server hello is the certificate exchange. The certificate exchange is that the server sends the client a list of X509 certificates to authenticate itself. So this is an entire chain of certificates from basically everything that the client would need to verify it. And then if the client has also requested the certificate validation, it's going to be included as well. So here's the certificate chain you can use to verify the CA that I used. And included in this is the public key, so you can send secured messages to me once you decide you can trust me. The next piece is the actual certificate status itself. This is the OCSB signed message that's used to authenticate the certificate that was sent. And it's known as OCSP stapling because the OCSP, the certificate status, is actually stapled to the certificate, so it's attached. Then an optional piece of the server hello is the server key exchange. It's only sent if the certificate provided by the server isn't sufficient for the client to exchange a pre-master secret. So in most cases, this does not happen. But for DHE, DSS, DHE RSA, and DH Anonymous, there's not enough entropy to generate keys, so that the server sends its server key. Server key exchange in detail. So we'll spend a little bit of time on the server key exchange, but basically you can use key exchange as part of the cipher suite only if the server key type and certificate match each other. So each cipher suite defines the key exchange algorithm that's going to be used, the symmetric encryption and integrity check that'll be used consequentially, and then the key exchange itself might be RSA. So the key exchange works by encrypting a random value with the server public key. This requires that the server public key is an RSA key, and that the server certificate does not prohibit encryption. And then there's DHRSA, DHDSS, DHE etc. We won't go through all of these. The server key exchange for elliptic curve crypto. So there's a different RFC around SSL TLS that defines the key exchange for elliptic curves. But the elliptic curves typically in use are elliptic curve Diffie-Hellman ECDSA, Diffie-Hellman RSA, elliptic curve Diffie-Hellman EC DSA, etc. And also some notes here about the actual server keys and cryptography that you may want to review. Diffie-Hellman DHE-RSA offers what's called perfect forward secrecy. This is a term that you'll hear a lot. Perfect forward secrecy means that if an attacker was to obtain a copy of the server private key, he's going to be able to decrypt past recorded sessions if those recorded sessions used that RSA key. The attacker is not going to be able to do that if the sessions use DHE-RSA, because DHE-RSA uses perfect forward secrecy. Perfect forward secrecy essentially ensures that the session keys, even if they're compromised, can't be used to recompute past session keys. You know, in practice, perfect forward secrecy actually doesn't offer that much additional security, because if the attacker has access to the server memory, they've already got everything that there is to get. Continuing with the server key exchange, optional components, certificate status, and OCSP stapling. Here's the actual Wireshark for that. You can dig into that if you like. Then there's the client certificate request. It's optional. It's sent when the server wants to authenticate a client. So do you have a client certificate? Please send it to me. Then the server hello is done. So the client response to the server hello is the client key exchange. So the protocol version continues the original negotiated protocol version. The pre-master secret now, the random from a client is encrypted with the public server public key. So there's additional information involved as well, but basically the client is now able to use the pseudo-random number and the server public key to generate a pre-master secret. The pre-master secret basically allows both sides to begin to share the same information. Once you exchange the pre-master secrets, you can compute the actual master secret and begin to pass messages. So this message contains the protocol version of the client, which matches what the server said it could do. The pre-master secret, along with the server and the client random number, it's used to generate the master secret. And now the client says, okay, now I want to change ciphers. I want to go from asymmetric to symmetric and begin to pass data. The client response for this last piece is called the encrypted handshake message. And the encrypted handshake message is, here is a hash, and this is an encrypted message. Here is a hash of all of the messages that went before, so that you can verify that I'm the client, not a man in the middle. The server responds by changing cipher as the client specified. So now the server flips over to the symmetric encrypted channel communication. It provides the client with the encrypted handshake as well. This is the encrypted hash of all of the preceding messages, so that the client can verify that the server is also who it said it was. And then the actual SSL TLS data flow between the two. So that was TLS 1.2. So now TLS 1.3. TLS 1.3 is fundamentally different than TLS 1.2. So why did we retire TLS 1.2? Well, TLS 1.2 is old, first of all. It was established in 2008. Most importantly, TLS 1.2 allows bad practices on the part of the administrator. One of the things that's still true is that TLS 1.2 can be made to be very secure and very tight, but it requires the server administrator, the administrators of the equipment, to actually know a lot about TLS SSL, and very often they're not so sophisticated about that. TLS 1.2 gets rid of many bad practices and defaults to a much more secure mode. TLS 1.2 also allows old ciphers that are insecure, and the TLS 1.2 handshake is unnecessarily complicated, as you've seen from all the stuff that went before. Outdated cryptography resulted in a bunch of vulnerabilities. You can read the list as you all do some research for yourself. There's many vulnerabilities in 1.2 and 1.1. The TLS 1.3 handshake compared to TLS 1.2, you can see is very, very different. There's up to sort of 10 different phases of the TLS 1.2 exchange, and TLS 1.3 has 3. Step 1, similar to the TLS 1.2 handshake, there's a client hello that the client sends to the server. It includes in that the cipher suites. It makes an educated guess about the key agreement and the key share. The server responds with a key agreement protocol, key share. Server says I'm done. The client then checks the certificates, generates the keys, and the client's done. That's it. That's TLS 1.3. So going into that in detail, you can see that the client hello in TLS 1.3 is much bigger than the client hello in TLS 1.2. So the client generates a key pair using elliptic curve asymmetry. The client random data is used later in the handshake. There's a list of cipher suites that the client supports that's included in the hello, a list of public keys that the server might find suitable, and protocol versions that the client can support. That's the client hello. So in detail, right, so the client random is 32 bytes of random data. It's going to be used later in the session. So then there's the session ID. In previous versions of TLS 1.2, a client could provide an ID of a previously negotiated session. That allows the client and the server to skip over the time and the cost of negotiating new keys. In TLS 1.3, that session resume is done using a different mechanism, which is the pre-shared key mechanism. So that field is no longer used for that. So that field is actually overloaded with a different value and different purpose called middle box compatibility mode, which helps TLS 1.3 sessions be disguised as TLS 1.2 so that it can tunnel through TLS 1.2 compliant but non-TLS 1.3 compliant middleware boxes. The cipher suites, so the client provides an ordered list of which cipher suite it's going to use. In TLS 1.3, the list of cipher suites is actually enumerated. For example, in this case, 0006, hex 6 bytes of cipher suite data is coming, and then it's 1301. 1301 has already been assigned a value for AES 128 GCM SHA-256. 1302, 1303. These are assigned values, and you can read up on those on Wikipedia. And then there's an extensions list. So here's a list of optional extensions that the server can use. This is all still in the client hello. So here's 77, hex 77, which is 119 bytes of data with extensions. Each extension starts with 2 bytes. It indicates which extension it is. And then here's detail. Here's an SNI extension. 00, that's the assigned value for server name. 18, so 24 bytes of server name extension. Then 16, 22 bytes of first and only list entry. And then the list entry is type 00, which is the DNS host name, and then 19 bytes of host name follows. And then there's the host name. So each extension is done in that manner. And then supported groups. The client has indicated that supports elliptic curve cryptography. And then here's an example, 1D1718, so it supports X25519, etc. The signature algorithms, this is another extension. You can read the list here, but for example, 401 is assigned the value of our SA public key CS1, SHA-256. Then there's the key share. The client sends public keys using an algorithm that thinks the server is going to support. This allows the rest of the handshake after the client hello and after the server hello to be encrypted. This is a big change between TLS 1.2 and 1.3. So then the client hello is complete. Now the server hello. The server generates a key pair using elliptic curve asymmetry. The server sends the server random data that used to be used later in the handshake. Session ID, the cipher suite is selected. The extensions are sent from the server and then change cipher. So you can already see we've got the client hello completes almost all the necessary data sent to the server. The server hello completes the remaining pieces missing, and then you're ready for a change cipher. So here's the key share. The server sends a public key using the algorithm of the public key sent by the client. Once this is sent, the encryption keys can be calculated. So 33, the assigned value is key share, 36 bytes of key share extension data. 1D means the assigned value of X25519, which means the key share exchange is going to be done via curve 25519. And then 20 hex 20, 32 bytes of public key, and then the public key itself. New in TLS 1.3 that we're not going to go into is that there's an option called 0 round trip time resumption. And that's good because it means that both sides can resume the previously established session without a bunch of back and forth. The bad is that there is no full forward secrecy on 0 round trip time resumption. So what that means is that if the session ticket keys are compromised, an attacker can decrypt the 0 round trip time data sent by the client. You can read more about that in the link on the bottom of the slide. TLS 1.3, the handshake key calculation. So there's two pieces needed. There's server key calculation and client key calculation. We're not going to go into this in detail, but basically at this point in the exchange, the client is hello, the client has said hello, the server has said hello. So therefore, the pieces that are necessary, the client public key, the server private key, the SHA-256 hash of the client hello and the server hello are present, so therefore you can do the key calculation on the client side as well as the server side. So the next piece is new. Very important to understand that following the hellos, the rest of the negotiation is done encrypted. So the TLS 1.3 records are encrypted to look like TLS 1.2 data records. So basically, if you are tunneling through a middleware box, it looks now at this point in the negotiation as if the TLS 1.3 handshake is actually TLS 1.2 data. Now the handshake finishes. So the next pieces are the server certificate chain and the server certificate verification. This is encrypted, and then the client handshake end. So that is a very quick overview of TLS 1.2, its retirement, and TLS 1.3. Thank you very much for your time.